All right, so today we're going to talk about the fundamental theorem of calculus. And with that name, it better be important, right? And it is. Remember when we were trying to compute the area under a curve? Let's draw our favorite curve. Something like that. And we wanted to compute the area under this curve in between, say, A and B. Well, we started by partitioning our interval into n rectangles. So n is going to be that right now. And we did rectangles and we increased. We could do upper, lower sums, or we could do left or right sums as well. And then we approximated our area through rectangles. So that was one approach we had. And then we said, well, whenever you do n many of them and you said the area, which we defined as the integral from a to b of this function, let's say y equals f of x. So the integral between a and b, or for f of x, was going to be given by the limit as n goes to infinity. And I'm going to write just the right sums just so we don't, I mean, we could just do, let's just do it, delta xi f of ci. Just a little bit more general there. So we did that. However, the limit process was quite annoying, and it seems to be a trend in calculus where we let you do things through the limit definition, and then we tell you, you know what, never mind, it's easier to do it this way. And this is pretty much the case of the fundamental theorem of calculus. And by the way, I'm talking about the second version of it, so I'm going in a sort of the wrong order, but this is probably the one you're going to be using the most, the one I'm going to mention right now. So the theorem basically tells you that if f is continuous on the interval a to b, and capital F is an antiderivative of f, then the integral from a to b of f of x dx, instead of being the limit, it's still the limit, but you don't have to compute it. You can use your antiderivative to compute it by doing f and evaluating it at b, and then doing f and evaluating it at a and subtracting those quantities. So this is way, way easier to use. So one example. So normally we do things with parabolas that open down. So say from -1 to 1, and let's do 4 minus x squared, for example, dx. And what would this represent? We can draw that real quick. Very small too. It'd be your parabola that opens down. It has y-intercept 4. And between -1 and 1, the intercepts are plus minus 2. So between -1 and 1, you're going to be going sort of there, and you're computing this area under this curve. This would have taken you a little bit of time to actually set up your sums, but now you just use your antiderivative. This is a polynomial. It's obviously continuous. It's continuous on the entire real line, let alone from -1 to 1. So there's nothing to do there but take the antiderivative of it, or an antiderivative. In this particular case, I'm going to pick c to be 0 for the reason that, for the simple reason that if I would add plus c here, then I would have to do plus c when I evaluate it at 1, and then minus c when I evaluate it at -1. So the constant, you'd end up with a plus c here and a minus c here, so it cancels out. So you don't have to write a constant, even though we've drilled into your head that you needed to do the constant. Now, this is a good time to talk about symmetries. This right here, this function is an even function, so it is symmetric with respect to the y-axis. So you could also say that this area here is 2 times and that would save you a little bit of trouble. This is going to be the same as 2 times the area from 0 to 1 of the same function. So if you want to, instead of evaluating at 1 and at -1 and subtracting it off, you just can multiply from evaluate at 0 and 1 and multiply times 2 at the end. Let me do that. So when I evaluate at 1, I get 4 minus 1/3, and then minus 0. I think I made a mess there. Let me do it the right way. Let me do it the way I had it here. I'm just going to leave that as a comment because I don't want to confuse you. So I am in disagreement with my own idea. So I'm going to evaluate it at 1 and then minus, and I'm going to evaluate it at -1. So 4 times -1 minus -1 cubed over 3. And we're going to get 2 times this anyways, because the negative is going to factor out and it's going to become plus. You see, both are odd factors, or odd powers. In any case, so 4 minus 1/3, you're going to have 12/3 minus 1/3 is going to be 11/3 minus, and if you compute this one, you're going to have -4 minus negative, so plus 1/3 is going to be again -11/3. When you add it, you get 22 thirds, so the 3 came up in my mind, I guess. So 22 thirds, which would be the same thing as what if we would have computed the first term and multiplied it times 2. All right, so we had several things going on. Firstly, we used the fundamental theorem of calculus. We checked that the function is continuous. And we evaluated the antiderivative between -1 and 1. Then I also told you that if you have a function that is symmetric with respect to the y-axis, meaning an even function, then you can always just evaluate from 0 to a. So if it would be from -a to a, from 0 to a, multiply times 2, and that would save you a little bit of evaluation. However, you can always do it not the right way, but this way. All right, so let's take a look at another example, and this one is fun because you see you have 1 over x is your function, f of x equals 1 over x. And that one you tend to think, oh, that's not continuous. However, that's not continuous at x equals to 0. So you're going from 1 to e. That's a way. So let's draw the graph as well. So let's just draw the positive side of that graph. So you have f of x equals 1 over x will look something like this. So you have your discontinuity at 0. However, we're going from 1 to e. E is 2.7 something. So yeah, I'm very precise. So you're looking at this little area here. So the function is continuous on that interval from 1 to e. There's no problem with that. So you can apply your fundamental theorem of calculus. So you integrate this here, which is going to give you the integral is going to be natural log of the absolute value of x, and you're going to evaluate it between 1 and e. And then you get the natural log of e, which is 1, minus the natural log of 1, which is 0. So you get 1 minus 0, which is 1. So that little area there happens to be of 1 unit square. I don't have any units, so I don't write anything, but if I had units, if this would be an application problem and I had units, I would have to then consider the fact that this is in fact an area, so the units would be squared. All right, that was a bit of a letdown of an example. It was too fast. Let's do another one. How about the following? Let's take a look at the graph of the cosine, for example. And I should have made it a little symmetric here. So let's start here at 1. Let's go down to pi over 2, where it goes to 0. And let's go back to pi, where it's -1. Not very, very symmetric. But let's take a look and let's try to find out what's the area of the shaded region. Now, you know there's symmetry here, so if you just do the fundamental theorem of calculus and you would just integrate from 0 to pi, the function which is the cosine, you would get 0 because this is a positive area, this is a negative. So you would get 0. So we don't want that. We want the area of the shaded region, so the question would be, let's find the area of that shaded region right there. And of course, you could use symmetry and say, well, I go from 0 to pi over 2, which is right here. And that's going to give me one area. I multiply it times 2 and I get the other one. But let's not cheat at the moment. So let's just write the area to be the integral from 0 to pi over 2. That's going to be the positive area. So I'm just going to write the fundamental theorem of calculus. I'm going to use that to evaluate this integral. So that's that. And then this one is going to be negative. So to turn it into positive, I'm going to subtract it off. So from pi over 2 to pi of the cosine of x dx. And you'll see that we'll get 2 times this one anyways. But it's but we're going to write out the whole integral because we don't need to have symmetry. The functions may be slightly different. If you don't have symmetry, then you do it this way. All right. So I evaluate here my antiderivative is just the sine of x. I want to evaluate it from 0 to pi over 2. And then minus the antiderivative of cosine, again, an antiderivative. So from pi over 2 to pi. And now we just evaluate here. So this is going to be the sine of pi over 2 minus the sine of 0. That's this one right here. And then minus, let's put in a parenthesis, sine of pi minus sine of pi over 2. So now sine of pi over 2, as you remember from your unit circle, is 1, and sine of 0 is 0. So you get 1 minus 0 minus 0 minus negative plus 1. Sine of pi is also 0, by the way. I didn't say that. And your area is 2 units squared. All right, so that's another quick application of the fundamental theorem of calculus. All right, so the integrals were not too difficult today, but the idea is that if the function is continuous and you can find an antiderivative of your function, you take your antiderivative and evaluate it at the right endpoint minus the left endpoint, the function evaluated at the left endpoint rather. So let's take a look at what is called the first version of the fundamental theorem of calculus. All right, so the first version of the theorem goes like this. So if f is continuous on an interval, let's say at, it's really on. So on the interval, and in this case I don't really need f to be the antiderivative. I need f to be defined in this way. So f is going to be a function that is going to take the value, it's going to be the area under the curve of f of x between a and x. I'm going to draw a picture to explain this. So what does that f look like? So if you have little f, and let's say a is somewhere here. Let's draw the same graph. And we say a is here. And then there's a b here. Okay? X is somewhere in between those. And I'm going to write that here. X is in AB. All right, so x is somewhere in between here. Okay? So what the function capital F is doing is just giving you the area under the curve y equals f of x. I had the right marker. So it's giving you the area under the curve. So if you were to move x again, so this area corresponds to capital F of x, that area. Now if you were to move your x somewhere here, let's say x1, and you compute the area all the way to x1, that area would correspond to f of x1. So the function f, so defined, all it's doing is capturing the area from a to whatever x you feed it. So if you feed a, f of a is going to be 0, and if you feed b, it's just going to be the area under the entire curve. So f, you just define it in this way. Then, that's not capital. It looks like it, but it's not. The derivative of f is little f of x. So in other words, Another way you could just state it, assuming everything is continuous and works out, the derivative from a to x of f of, let's say, t dt. By the way, yeah, it's kind of bad manners to put x here, huh? Let's change that to t dt. Because x is already an endpoint. Much better. All right, so if you take this derivative, that should just be f evaluated at x. All right, so let's do a couple examples for this one, and then we'll wrap up the video there. All right, so let's compute this derivative here. So firstly, you do not know how to take the antiderivative of this function yet, t natural log of t. In a couple of lectures, you will learn, or actually no, a little bit later down the semester, even though I recorded the video yesterday, you will learn how to do integration by parts, and you would be able to do that with integration by parts. But at the moment, you don't even know how to take that antiderivative just yet. So it looks crazy that now I'm asking you to calculate the derivative of this function that uses that integral right there. So, but using the fundamental theorem of calculus, this is really easy, because it says, well, when you take the derivative of this function, so this is my capital F of x, when you take the derivative of that, which is what I'm doing here, I get little f of x. So the inside function just evaluated at x in place of t. And that's that. Of course, I forgot to tell you that the function is continuous from 1 to x for any x. Because remember that the discontinuities for the natural log occur at 0 and to the left of 0. Anything to the right of 0, the natural log is continuous, so you're good. So this right here, starting at 1, it's all right. All right, so let's do another one. All right, so let's take a look at this one right here. If you notice here, this antiderivative is another one we don't know the antiderivative of e to the t squared, but we don't need to, right? But now notice one thing, that if I define f of x to be the integral from 0 to x of e to the t squared dt, then what I have right here is nothing but f of x squared, because I changed the x for an x squared. So what I need to do then is take the derivative of f of x squared. Notice I have two functions. I have f and I have the square function. So this, when I take the derivative, I should use chain rule. So what that tells me is derivative of the outside, f prime, evaluated at the inside, x squared, times the derivative of the inside. Now, I know that f prime of x by the fundamental theorem of calculus is just f of x. That tells me that f prime of x is equal to e to the x squared, just evaluating the function inside of the integral at x. With that then, I get that this derivative that I wanted, which is just the derivative of f of x squared, is going to be equal to f prime, which is little f, evaluated at x squared times 2x. So I'm going to get this function evaluated at x squared, which is going to be f prime. The space is not going to work for me there. Anyways, I'm going to write it out, times 2x. I made a little bit of a mess, didn't I? Let me just write the answer here. F prime at x is e to the x squared. F prime at x squared is going to be e to the x to the fourth times 2x. So in effect, what did I do? I just evaluated that x squared into here, but since I was not evaluating it at x, I paid with the chain rule, which is the derivative of this x squared. So the derivative of this x squared became 2x. I plugged it in. I get e to the x to the fourth times derivative of it. So whenever you are taking the derivative of something that it doesn't go from, say, a to x, but a to a function of x, you plug in the function of x into the t, and then you pay off with multiplying times the derivative. That would be an application of your chain rule. Let me do one more of those just to clarify. All right, so now the last example. So what I said was, you grab your function of x that is on the endpoint, plug it into your t. So you get sine squared of x cubed. But then you're not plugging x, you're plugging x cubed, so your chain rule tells you have to multiply times the derivative of that endpoint. So 3x squared, you multiply times that, and that's your derivative. All right, we'll wrap it up here for this video, and I'll see you in the next one. Thank you.